Welcome to the session on echolocation and consciousness. So the philosopher Thomas Nagel asked famously, what is it like to be a bat? By which he, I think, basically meant, what is it like to echolocate? To find out the positions and movements of things in your environment by this broadly auditory facility of sending out sounds and processing them. Well, today we're going to find out. We have a terrific panel of people who have thought about echolocation in humans and animals from a number of different perspectives, including first person and third person, practical and scientific perspectives. We have one person who echolocates. We have one person who studies echolocation in humans, and one who studies echolocation in non-human animals, especially bats. So I think this is going to be a terrific perspective on a really intriguing topic. It's been a tradition at the Tucson conference to present not just third-person scientific perspectives on some of these interesting syndromes of consciousness, but also first-person perspectives on these topics from people who can tell us, after all, how do you find out about states of consciousness, either that are not your own? Well, the best way we have is to ask people and to get their verbal reports and their descriptions of their own states of consciousness. So it's particularly important, so it's particularly valuable to have here today Daniel Kish, who has a lot of first-person experience of echolocation. I gather everybody has some first-person experience of echolocation, and maybe this will come up. But Daniel has really developed this to an art form. So Daniel is CEO of the World Access for the Blind, and has been over for many years now developing all kinds of tools and methods for blind people to access the full range, or manifest as much of the potential of human perception as possible. He's got degrees in developmental psychology and special education. He's been working with, he's been doing his own pilot research on these things, as well as collaborating with schools and families and agencies and so on, and has been developing any number of initiatives and programs, including the initiative of flash sonar, which I'm sure we'll be hearing about, for working with blind students to enable them to develop the full range of perception. So he's done really very important work, both on the helping us to understand this phenomenon both practically and theoretically, and really making a difference socially. So it's a great pleasure to welcome Daniel Kish.
It's not just yet. Yeah, we'll start. No, it's fine. Okay. So, what is it like to be a bat? I was actually asked that. Someone wrote to me, and they were having this discussion in a philosophy course, and he introduced me to the whole Thomas Nagel thing, and asked if I could shed any light on what it might be like to be a bat. And I asked him, what would it be like to be a hawk? And so as a human echolocator, I don't know that I have any more of an idea what it's like to be a bat than a sighted individual necessarily knows what it's like to be a hawk. I know that bats have extremely adept, extremely refined echolocation capacity. An echolocation capacity that humans are not likely to equal, at least not without substantial technological assist or even surgical assist. I've also been contacted by people who asked if it might be possible to surgically, or actually to suggest that it might be possible to surgically alter one's ears to improve one's spatial auditory acuity. And I would want more evidence-based before someone went and surgically altered my ears. but I think it's an interesting prospect. I think what I'll do is go through some demonstrations of what the echolocation process might be like. I can give you all some first-hand experience, a first-hand example of what the echolocation process is like, so that you walk away with a sense of it. But I think that what I will do is start with the video, if we could. And it's on Cynthia's computer. So she's going to go ahead and play a video that not only gives you a little bit of an introduction to the echolocation process, but also gives you a little bit of introduction to our work in particular.
It seems we have no sound.
Oh, do we still have no sound?
He's coming up here.
Okay.
Sound on laptop? On?
What I'll also do a little bit later on in the talk, someone asked me last night, and I get asked this on a fairly regular basis, what is it like to perceive your environment as a blind person? In particular, what is it like to be able to gather information from your surroundings, to gather spatial information from your surroundings as a blind person? And likewise, I like to put that back into the hands of the people who ask. What is it like to see? What is it like to gather information visually? How easy is it to answer that question? I do, however, have an answer to the question of what it is like to gather information as a blind person. Okay, so this, let me give you a bit of an introduction.
Sono qua, Juan.
So start this from the beginning. So basically, this is one of our colleagues. He is now an instructor. I began working with him when he was 12 years old. And he, obviously he echolocates, as you'll see. And we, World Access for the Blind, were asked by Guinness World Records in Italy if we could set a record. And I asked them, what kind of record? What did you have in mind exactly? And we went back and forth, and I decided to send Juan to them because I didn't really want to do it. And you'll see what kind of record Juan sets. But in addition to Juan setting this record, Juan also works with families to help them, to help their children develop these kinds of skills. He worked with families in Italy while he was there. He's recently worked with families in Honduras. And he and I will be traveling to Austria to work with families and schools for the blind there. So we'll go ahead and play that. We'll go ahead and play that video, and I'll fill you in on the rest afterward.
Juan Ruiz. Eccomi. Sono qua, Juan. Welcome.
Buongiorno.
Welcome.
Gracias. Thank you.
Che cos'è l'echolocation? Come funziona?
Sound waves bouncing off objects.
Praticamente con questi segnali che io emetto riesco a capire dove sono gli oggetti.
Listen.
Ascoltate.
This obstacle course here that I'm going to do today
Questi ostacoli che cercherò di superare oggi
is not just poles.
non sono semplicemente dei pali,
It is a goal.
è uno scopo.
And the bigger the goal,
E se lo scopo è molto grande,
the bigger the more obstacles you'll face.
più ostacoli dovrai affrontare.
And on the other side of that goal
Dall'altra parte, nonostante gli ostacoli,
is victory.
c'è la vittoria.
And if you should fail the first time,
E se c'è un fallimento all'inizio,
you should get up and try again.
ti devi rialzare e ci devi riprovare.
Juan, are you ready? Yes. Okay, start at my go. 3, 2, 1, go.
È partito,
Parte il tempo.
sentite, il pubblico sta in silenzio per poter permettere al giovane messicano, ormai residente negli Stati Uniti, di poter quasi come un sonar localizzare i pali. Avete visto? Adesso non sapeva dove fosse questo, ma lo ha localizzato. Perfetto, perfetto. Signori, probabilmente sarebbe difficile anche vedendoci una cosa del genere. State vedendo un ragazzo non vedente che sta superando un Guinness World Record.
Stop.
E allora! È stato bellissimo vederlo, Juan. Vieni con me, andiamo al centro, my friend, mio amico.
Doveva percorrere questo percorso in meno di 53 secondi e lo ha terminato in 48,34 secondi ed è un Guinness World Record!
Voglio metterlo io. Scusami, Marco.
Do you okay, if you can get that one to work, that's fine. So, I taught him how to do that. Actually, I should be clear. I taught him how to echolocate. I did not teach him how to do that, okay? And in fact, that was only his second time doing that particular kind of task. And of course, the obstacle course was not the same. You saw them changing it on stage even before he reached it. So he never actually had a chance to practice that particular obstacle course. But he did have a chance to practice that particular task only once before. Okay? So the idea here is that the echolocation process, like the visual process, is transferable. It's generalizable. One can apply it to other kinds of skills, to other kinds of perceptions. The style of training that blind people tend to receive traditionally focuses on the learning of particular kinds of skills.
Excuse me, Daniel, it's not playing sound in any format.
Right, okay. That's okay. We tend to teach blind people how to exercise certain skills under certain circumstances and certain activities. The approach that we take is to back off of skills training, what I call mechanics training, and focus on perception training, the development of perceptual abilities that one can apply to learning any kind of skill that one can feasibly do using the kind of perception that we're talking about. So the question we might ask is, how could one do that? How could he do that particular kind of skill using just a tongue click? We're talking about a person who has no usable vision, doing this kind of a task on a live stage in front of a live audience in an environment and under circumstances which are in many ways less than optimal, okay? And I'll answer that question actually with a demonstration. Instead of using pylons, I'm going to use this laptop here. This is not an advertisement for Apple, although I think I should be collecting royalties by now. This is just a prop, okay? It might as well be a serving tray. In fact, a serving tray would actually work better, but this will do the trick. So let's pretend that this is one of those pylons, one of those poles that Juan had to navigate around and betwixt. And what I'm going to do is I'm going to make a continuous sound, a sound, and watch what happens as the prop passes in front of the sound. You might actually close your eyes to hear this more effectively. Okay, could you hear a difference? Okay, so you can hear the sound changing as the prop comes in front of my face and then goes away. And in fact, if you listen carefully, the whole prop doesn't actually have to pass. You can hear it approaching just at an edge. Okay, so I only have to be about an inch into the process, into the prop for you to be able to hear the difference. Okay, and so what we have here is an individual, say a blind person who's using echolocation. He passes a column or a pillar or a pylon. He hears the edge, and then hears the pylon pass by. It's basically, it's an acoustical version of a flow field. It's an acoustical flow field. Just as you have an optic flow field, you have an acoustic flow field. So you flow past objects in your environment. Okay? You're also edge detecting. So not only can an individual tell whether something is in front of them or beside them and where the edge of it is, an individual can use this edge detection capacity to actually trace the contours of an object. Okay? So it could be a parked vehicle, it could be a bush, it could be a tree, it could be just about anything with reasonably defined contours. And an individual can use this edge detection capacity to trace those contours and to interact with objects in a precise manner. Okay? So as Juan was navigating his BMX bicycle through this obstacle course, he was identifying the location of these pylons, okay, with a degree of precision that was necessary for him to both find the gaps between them and to actually avoid knocking them over. Okay? Now, but there's an additional quality that needs to be present here. He needs to know not only where the edges, the boundaries of these pylons are, he also needs distance information. He needs the ranging process, which is endemic to echolocation. Okay? Echolocation is actually very, very good at ranging. Sonar sounds for sound navigation ranging, right? So here now, if you close your eyes for a moment, I'll do a different demonstration, which will be a distance task. So I'm going to make the same kind of sound. I'll make that sound continuously without changing the nature of the sound or the timbre of the sound itself. But you will hear the sound change as I move this computer toward my face and away from my face. So I'll start with it at arm's length, and I'll shh for a bit, and then you'll hear a change in the sound. Okay? Could you all hear that? Let's make sure. So we'll do a little quiz, okay? So what I'd like you to do is close your eyes. And I'd like you to just listen for a moment. I'm going to shh very relaxedly for a while. And then at some point, I'm going to start to move this computer. And I'd like you to indicate by saying now or something else. You can say anything you like as long as it's polite. When the computer starts to move. And we are going to just relax into this. I've had people scream now or stop before I even began shishing, okay? So we'll just ease into this. Thank you. All right. I didn't have to bang myself in the head with this computer. Excellent. Okay. One more time. One more time. Eyes closed. Good. All right. So, nicely done. So if you open your eyes, we've moved from here to about here, less than a foot. Okay? Now, experience tells me that even if I had this microphone off, with a panel this size or a bit larger, most of you, in at least the forward half of the room, would still be able to hear this. Okay? So if you think about this, without any training at all, without any formal experience, without any conscious awareness of your own echolocation capacities, you were able to hear a displacement of a surface of less than 12 inches, with the surface being, well, this size, okay, not particularly large, 15 by, I don't know, 8 inches or something, 13 by 8 inches. The process isn't that difficult, surprisingly. We have taught hundreds and hundreds of blind people all over the world to be able to do this to varying degrees. We've even taught a few sighted people. A lot of variation among sighted people in terms of capacity. But I think that this process, this ability, is hardwired. I think it's an ability that we have. I don't think it's an ability that we have to make happen. I think it's an ability that is dormant, ready, and waiting to happen. It just needs to be activated. So Juan, doing his little stunt for Guinness posterity, basically was using a combination between distance and edge detection information to be able to accomplish that task in a similar manner than you guys have done here today, with one exception. With Juan, he's not only hearing the differences. He's not just saying to himself, okay, this sounds like this, therefore I need to maneuver my bicycle this way, and that sounds like that, therefore I need to maneuver my bicycle that way. The sound, the acoustical calculations that are happening are actually mostly unconscious, probably. What is conscious in his mind, though, are the actual images, an actual image representation of the obstacles that he's navigating. It isn't just a sound signature. It's a kind of image experience, okay? So when a person who's echolocating is imaging, they are essentially constructing an image out of 3 characteristics that they may or may not be conscious of. When we train students, we train them to be conscious of these characteristics. But these characteristics eventually become more and more unconscious. You're looking at location. Where is the item or feature or object relative to me and relative to other items or features or other objects. Okay? Where is it? Where is it laterally? Where is it vertically? Where is it distally? Is it in front of me? Is it behind me? And how far? Dimension, having to do with the geometry of the object. Its edge geometry, if you will. How tall is the object? How broad is the object? Is it broader than I am? Is it narrower than I am? If it's narrower than I am, is it a lot narrower or just a little narrower? A lot wider or just a little wider? What are its contours? Where are its edges? There's one exercise that we do, which if you Google around enough, you'll find this video, where we have students trace the outline of a car. So you look at the car, you click at the car, you determine which is the front end and which is the rear end. Okay, how would a person who's echolocating know which the front end of the car might be versus the rear end? Anyone want to answer?
Real headlights.
Headlights. What else?
Windshield.
What about the windshield?
Echolocating the windshield, the slope of the windshield.
The slope of the windshield, okay, okay. Getting closer, what else? What's that? The mirrors, okay.
The hood is lower.
The hood is lower, all right. It's kind of all of the above and more. The slope of the windshield is likely to be more gradual in front than in back. The hood is likely to be lower in front than the back. It's also likely to be longer, okay? Rear view mirrors, more difficult to detect. This is actually where cognition comes into play. I was in the UK, and I was traveling with someone. She was another mobility specialist. And we were traveling along the sidewalk, and we passed a few minivans or something. And she made the remark that a friend of hers, who was blind, said the bane of his existence are these rear view mirrors that stick out of sports utility vehicles or vans. They're about head level, or possibly shoulder level, depending on your height. And you whack into them every time. Your cane doesn't detect them, right? And she said, there's no way for a blind person to detect these. And I said, well, actually there is. Even if an individual who is echolocating had difficulty detecting those, and there's reason for that. There's reason why those things are difficult to echolocate casually. Because with echolocation, you have a bit of difficulty with figure ground, meaning that differentiating one object from another if they're close together, okay? But it is easy, simple, to echolocate the fact that there is a minivan there. That's not hard. You can do that casually. You can do that while in the middle of a conversation with your loved one, maybe, probably. For some people, easier than others. The point is that by casual observation, you can tell that you're passing something the size of a minivan, okay? And if you know that that's what it is, then you can direct your attention to where the rear view mirrors may be and avoid them that way. Okay, anyway, so back to the car. Once you've identified the front of the car, you take your hand and you hover an inch or two above the car and you trace its outline. You go up the bonnet, the hood, over the windshield, across the top, and down the other side. And everyone goes, ooh, ah, because you've been able to do this, okay? That's an example of edge detection, of how the contours of objects may be perceived and interacted with. And the final is depth of structure, or for a long time I called it density, because every time I say depth of structure, people always ask, what do you mean? And then I say, well, we're talking about density, we're talking about the depth of structure of surfaces throughout the object. So is it dense? Is it solid? Is it highly reflective? Or is it sparse? Like a bush would be sparse. A stone or a boulder would be solid. A fence would be sparse, but a wall would be solid. Okay? Or is it absorbent? okay? A person wearing clothes, for example, would be much more absorbent than a person not wearing clothes. So basically, those are the three main characteristics. Texture as well. To some degree, you can get surface texture. Okay, how smooth a surface is versus how rough a surface is. Using natural echolocation, the surface would have to be relatively rough for it to really register as being rough relative to a smooth surface like glass. And that's basically it. There is no color. There is no sense of color. There is no concept of color. For individuals who have seen before, there may be an imagination of color, but it will not correspond to characteristics of the actual object. Most of you will have a hard time imagining a completely colorless image. There is no grayscale. There is no black. There is no white. There is no color. Imagine seeing out of your elbow. What would you see? I don't know. You wouldn't see anything. You wouldn't see color. Okay? That's basically all I have to say about that. I can take a couple of questions and then we'll move to the next person.
Okay, we can take a couple of questions now, and then we'll have a bunch of time for discussion at the end. Okay, I see somebody back. See someone there and someone there.
It was a wonderful discussion. How important is it for the person to generate the sound internally? That is the analogy to touching something with your hand as opposed to the cane versus producing the sound from another instrument as opposed to your own voice.
Okay. I think the key here is self-control over the process. Obviously, touching something with one's cane, you're getting conductive information, whereas touching something with your hand, you're getting actual sensory information. So there's a difference there. But I do have control over the cane, and as it comes into contact with things, the edge of the stage, for example, and this nice little piece of foliage here, I know what those are based on conductive information. I would know a lot more about them if I actually touched them, you know, with my hand or my foot if I were barefoot. In terms of using an instrument or a device relative, as opposed to a tongue click, I think that one could imagine creating a device that issued sound waves, signals, if you will, that were more, that could possibly solicit more information. It is important to note, however, that when one is in control of the production of one's own signal, the brain is ideally primed to receive information from that signal. You cannot fool your brain. You cannot do anything without your brain knowing about it first, okay? So if you're producing the signal, your brain's already ready. Also, if you're producing your own signal, your brain is highly attuned to the signal that you're producing. So many people will make the argument, well, why not just use passive echolocation? Why not just use sounds that are incident to the environment? And you can indeed do that. There are plenty of sounds incident to the environment that one can use for echolocation. We call that passive echolocation because the individual isn't actively producing their own signal and is not actively responding to the signal that they produce, is not necessarily tailoring their signal to the requirements and parameters of the situation that they're in. So in producing one's own signal, one is much more active in the process of gathering information from the environment and interacting with that information.
Okay, next one there. and then we got one just in front.
I noticed that you used a shing sound, more like a white noise, but you also show using a clicking sound. Do you vary the type of sound? Do you get different information depending on the type of sound you're producing?
The sh sound is generally done only for demonstration. So the clicking sound is the sound that would primarily be used. The timbre typically remains very much the same. It's the intensity, the amplitude that changes. So there are a variety of reasons that a human, now bats work a little bit differently, but a human will alter the rate of clicking and the amplitude of clicking depending on the activity in the situation. I have known self-taught echolocators who also altered the timbre, and that's fine, that works for them. I might say that that's actually quite an advanced use. It's easier, however, if you're using a signal that your brain has already highly tuned to, because the brain can much more easily filter that signal, extract that signal from noise. Echolocation is a trick. It's a trick of constantly extracting the echo from noise. It's a signal-to-noise trick. Okay, so the more familiar you are and the more attuned you are with the signal you're using, the easier that filtration becomes.
Okay, our last one for now from Kevin.
Do you find that in order to learn this skill, it's better to really think about the aspects of your auditory signal that you're getting and to understand each individual aspect? Or is it better for the process to become automatic, not to really think about it? And, for example, are children better at learning this than adults because they just do it without thinking about the actual cues that they're using?
We try to make the process conscious before making it unconscious. So you want a conscious competence before you reach an unconscious competence. We do work on sound signatures in the sense of, I don't usually concentrate on the sound feedback itself. I usually concentrate on the environment in terms of the objects themselves. So instead of talking about what it sounds like, I tend to talk about, or I tend to get the students to talk about what the object is like. Is it tall? Is it short? Is it wide? Is it narrow? How do we know? Now, when we ask how we know, then we may talk about the sound, okay? We do try to help students develop a language around their experience, because although sighted people have a very rich language around visual experience, blind people tend not to have such a language because that language isn't accessed within the culture. It isn't valued within the culture, okay? So I've had students come to me and say, well, you know, sometimes I think I can hear walls, but my mom says that's stupid. Well, how likely is an individual then going to share with others their experience with their environment? And indeed, how likely is such a person going to feel supported in developing such skills? So we do try to develop language, and we try to develop that through discussion, but it tends to be more in terms of one's experience with items and objects in question, and not necessarily so much in terms of the technicalities of the sound signatures themselves.
Okay, thank you very much.
Thank you.
Okay, our next speaker is Laura Thaler. Laura has her first degree from Bonn and a PhD from Ohio State University on a representation-based approach to visually guided motor behavior. Her research is all about determining how the nervous system computes and represents three-dimensional spatial structure from sensory information, and as a special case of this, she's become one of the leading experts on echolocation, especially in people. She's been working with a number of echolocating subjects, especially Daniel here, to try and understand this phenomenon from a scientific perspective. So please welcome Laura Thaler.
Good morning. So Daniel just demonstrated to you how echolocation works, what it can do. I'll start my talk by just showing you some illustrations of echolocation signals that people can use. What we did to generate these illustrations here was we went into a room, we had a loudspeaker, the loudspeaker made a click, and then we had various sound reflecting surfaces which were placed in front of the loudspeaker one at a time, and then we just recorded the whole thing. So in each of these illustrations, the first wiggly bit is an illustration of the click. The second is an illustration of the echo. Now if you look closely at all of these plots, you'll notice that the click in each of them is the same, which is because it was a standardized sound made by a speaker. The second bit, however, the echo changes, and it changes as a function of the surface that reflected the echo, or that generated the echo. For example, if you compare the top left and the top right two conditions, you'll notice that we just changed the shape of the surface by having on the one hand a concave surface and then on the other a flat one. And as a function of that, the envelope of the echo changes its shape. The same is the case when you look at the two bottom conditions. The only thing that's different here is that these were smaller surfaces, but the change in shape from concave to flat also produces a change in the shape of the envelope of the echo. Now if we compare the top left and the bottom left, the only thing that changed was the size, and as a result of that, the size or the amplitude of the echo changes. And this happens regardless of shape. Finally, there's also a little demonstration for the effects of distance. When a surface reflects a sound, the delay between the source sound, here is the click, and the echo will depend on the distance of the sound reflecting surface. And so here in the top, the surface was played at roughly 3.5 feet. And in the bottom at roughly 5.5 feet. And as a result of that, the echo delay changes. So there's a lot of information in echoes. Now, I'll play one of these sounds for you, so you get an idea of what they sound like. Did you hear that? Oops. I'll play it again. Now my question for you is, how many sounds did you hear in each of these little bits? Yeah, in total you heard 5. But in each of these little bits, did you hear 1 or did you hear 2? Okay, show of hands, who heard 1? All right, show of hands, who heard 2? Okay, you're good. Typically, people will hear only one of the sounds, even though I played you 2, the click and the echo. The reason that the majority of people will hear only one of them is that the human brain is kind of wired or set up to suppress echoes. And this is also termed the precedence effect. The precedence effect is a range of phenomena which describes the perceptual effect that if people hear 2 sounds in rapid succession, the percept is typically biased by the first sound. So basically, as a standard setup, the human brain tries to get rid of echoes. However, evidently, echolocation experts use or make great use of these echoes to infer lots of spatial properties about the environment. And there's also a lot of research showing that people can echolocate. In fact, past research has shown that people can use echoes to determine a variety of spatial characteristics of the environment, such as, for example, the distance of sound reflecting surfaces, their horizontal position, shape in 2D and 3D, materials size, and motion of sound reflecting surfaces. What I'm going to focus on today is, well, what are the brain areas involved? The reason we ask this question is out of scientific curiosity. At this point, we know relatively little about it. But also, the goal is perhaps that if we better understand the neural correlates of echolocation, we can perhaps optimize the skill and the way people learn and use it. Okay. So to investigate the brain areas that are involved in echolocation, we use functional imaging and specifically magnetic resonance imaging. To do that, you need a giant magnet. And this is what you see here in this picture. So it's a big structure, and in the center of it is a tunnel. To measure brain activity, the person has to be put into this tunnel. The tunnel is typically very narrow. Ours is 60 centimeters in diameter. And the person goes inside. And then on the right side here, you see a picture taken from the perspective of the feet of the person. And you hopefully get the message from this picture that it's just a very confined space. So in a way, we have then picked a tool to measure brain activity that's kind of unsuitable for echolocation because it's very tight, so there's not much to echolocate inside the scanner. So we had to come up with a way around this. And the way we did this is that we decided first, with each of our echolocation experts, to go outside in the world where there's a lot of space and make recordings of the actively generated echolocation sounds and the echoes. And then we go back into the MRI scanner and play these sounds back through headphones. And while this is happening, we were then measuring brain activity. So the first study that I'm going to talk about is one where it was the very first one, where we wanted to investigate, well, which brain areas are involved in echolocation, or which brain areas show activity that's related to echoes. We had two participants, one early blind and one late blind participant. Here you see anonymized pictures of each of the two participants while they were outside in the world and echolocated various surfaces. For this study, we chose a car, a tree, and a pole. So the person, each person stood in front of each surface and made clicks and explored the object. And while they were doing so, we made recordings in their ears. The recording therefore contained a lot of background sounds, like birds, leaves rustling, the clicks, and the echoes. And these recordings were individualized because we made them separately for each of the two people. Now, what we also needed were control stimuli. So what we did is we asked each of the two participants to stand in front of each surface silently. We recorded this. And then we inserted empty clicks into this recording. And empty clicks were clicks that we had recorded previously with each of the two participants in a special room that does not generate any echoes. And what this achieved was that we had a control sound which had all the background sounds as well as clicks, but no echoes. Now, in the scanner, we played all of these sounds back, and we asked each of the experts to indicate whether they perceived a car, a tree, a pole, or nothing, which would be the control sound. Each expert listened to both their own recordings and those recordings of the other person. And when you check the performance, it's evident that both participants could perform this task very well. That means they could reliably perceive the structure of the object from which we had made the recordings, the car, a tree, a pole, and they could do so even when the recording was not their own. Now, what are the brain areas involved in this feed? So what we did is we identified those brain areas that were more active during the presence of the echoes as compared to the presence of the control sounds, and that were also more active during the presence of the echoes than during silence. On the left side, we have various brain pictures for EB, and on the right side are the results for participant LB. Now, highlighted in white are brain areas that are referred to as calcarine cortex. These are typically brain areas that process light in sighted people. And remarkably, for both echolocation experts, these areas were more active during the processing of echoes than during any other condition, the control condition. Also very interesting, for the same comparison, we did not find any differential activity in auditory cortices, which are highlighted in this figure here in magenta. This led us to conclude that neurostructures devoted to vision rather than audition appear to be involved in the processing of echoes in these two blind echolocation experts. So if echolocation then is supported by visual cortex, we had many other questions about how this actually works, how all this is wired up. One thing that we were wondering about is, in visual cortex and calcarine cortex in particular, you typically find that you get a higher neural response when visual stimuli are presented in contralateral space. In other words, left visual cortex will give a higher response towards stimuli presented in right visual space, and right visual cortex or calcarine cortex will have a high response to stimuli on the left side of space. So what we were wondering as well, does echolocation exhibit this contralateral preference as well? To answer that, we conducted recordings where an object was presented to the echolocator either to the left or to the right. They echolocated the surface and we made the recording. Then we went into each of their brains, specifically calcarine cortex, and we selected areas in calcarine cortex that had responded to echoes in general, regardless of the position of the object. Then we analyzed the response of calcarine cortex towards echoes from a right or left presented object. Now, if there was contralateral preference, we would expect the following pattern of results. We would expect a higher response in left calcarine towards an echo on the right, and a higher response of right calcarine towards an echo on the left. Remarkably, for EB, we did find this pattern of results. In other words, we found evidence for contralateral preference for echolocation in calcarine cortex. We did not find this pattern in LB, the late blind participant. Now, another question that we had as well, is this activation of visual cortex actually echolocation specific? There's a lot of research showing that, in particular, the visual cortex in blind people is activated through stimulation in other sensory modalities, such as touch or regular spatial hearing. So in the study that I'm now going to talk about, what we did is we compared echolocation to regular spatial hearing. We had two participants, EB1 and EB2, both early blind echolocation experts. EB2 had less echolocation experience than EB1. We made recordings of echolocation stimuli where a surface was presented either to the left or to the right and it remained stationary. And we also included recordings where the surface was moving to the left or to the right. We made spatially matched recordings for source sounds as well. In this case, the participant did not echolocate. Instead, we moved around a speaker or held it stationary, and this speaker made clicks. Now, during fMRI, we presented these sounds to our participants. We presented to each echolocation experts both their own sounds as well as the sounds that were recorded in the other person's ears. And the task of the participant was to indicate whether it was a right stationary, a right moving, a left stationary, or a left moving sound. Both participants performed this task very well, both for the echolocation recordings and the source sounds. Now, in terms of brain activity, we then compared, well, which brain areas are more active during the echolocation conditions as compared to the spatially matched source sound conditions. And lo and behold, in both participants, again, we found that calcarine cortex was more active during echolocation than during source sounds. So again, it seems that this result confirms our findings from the first experiment, specifically that visual cortical areas are involved in echolocation. Now, a hallmark of visual cortical processing is that there are neural structures that are sensitive to smooth motion. It's a very distinct feature of the visual system that it has these special areas. And these areas are also called area MT+. Now, what we are wondering, are there echolocation motion areas? And also, how do these correspond to the visual motion areas? In sighted people, you find a typical arrangement between visual and auditory motion areas, such that visual motion areas are located typically somewhat behind and below those areas that process auditory motion. There's some variability between subjects. However, it is a typical finding that there are different neural substrates for visual motion and auditory motion. Now, in our blind echolocation experts, we have no way of testing this because we cannot present visual motion. However, we can use this relative arrangement between areas that process source motion and visual motion in sighted people, and then compare that to the relative spatial arrangement of auditory motion and echo motion in our echolocation experts. Now, the first step, we just reran the experiment that other people had done before, just to confirm that we get the same result. And this is the result here shown on the right side in sighted participants. So we have distinct areas for visual and auditory motion processing. So then the question is, do these areas correspond to echo motion and echolocation experts? The stimuli that we used for this experiment were the same as I presented before. We had echolocation stimuli that were stationary and moving to the left or to the right, and the same for the source sound stimuli. Now, here are the results. To the left, results for EB1, to the right for EB2. In yellow, we have the brain area sensitive to source motion, and in blue, the brain area sensitive to echo motion. In both participants, we find that we have different areas that selectively respond to echo motion or source motion. Moreover, the relative location of the echo motion areas seems to resemble the relative location of visual motion areas in sighted people. So this may suggest then that in fact these areas correspond to area MT+. Now, another way to test this, if the echo motion areas are in fact the analog or maybe the homolog of area MT+ in sighted people, is to again test for contralateral preference in these echolocation motion areas. In visual area MT+, you find preference for motion signals presented in contralateral space, such that left area MT+ will show a higher response to motion in the right visual field, and right area MT+ will show a higher response for motion in the left visual field. So what about echo motion? Here are the results. We do find evidence for contralateral preference in both EB1 and EB2, such that in both participants, we find a high response in the left echo motion areas for right motion or motion in right echo space. And we find a higher response in right motion areas for echo motion in left echo space. The result, however, is only significant in participant EB1. In EB2, there's a trend, but it's not significant. So it appears then that the spatial arrangement between echolocation motion and source motion areas resemble those that we find between visual motion and source motion in sighted people. And the echolocation motion areas show contralateral preference. This then taken together is consistent with the idea that indeed the echolocation motion areas may correspond to visual motion areas. To sum up all the things I showed you, echolocation appears to involve visual cortical areas. We have now found evidence that cricoid cortex as well as area MT+ may be recruited during echolocation. Echolocation elicits spatially organized patterns of activity that resemble those that we find in vision. The patterns I refer to here are specifically the contralateral preference patterns. The big question is, well, what drives these similarities? What are the underlying mechanisms? My favorite hypothesis or my favorite potential explanation is that perhaps visual cortex is implicitly multimodal, that perhaps visual cortical areas are spatial areas. And that is just the case that perhaps in most instances, this spatial information or the information that's necessary to perform these spatial computations is provided through vision. But that, in principle, other modalities can provide this information as well, such as echolocation. So now it's a conference about consciousness. And even though we haven't touched upon the issue of consciousness in our research to this point, there are things that we can speculate about. Now, it is known that we can use activity patterns in visual cortex in sighted people to predict the state of their visual consciousness or what they visually perceive at any given moment. There are reviews about this, and one of them is mentioned here on the slide. Remarkably, we can use activity in visual cortex to predict the content of visual consciousness even when there's no visual stimulation, or in cases where the visual stimulation is uninformative. So in this way, then, the brain appears to be, or at least the activity in visual cortical areas, seems to be a better predictor of consciousness than the actual physical world. So, echolocation elicits activity in visual cortical areas. Then the obvious question, I think, arises, can we predict the state of echolocation consciousness based on activity in visual cortical areas? It's very speculative. At this point, we don't have data, but maybe in a while. Another question that arises is, well, how do neural states correspond in visual cortical areas between people that use vision and people that use echolocation? I want to acknowledge the help of my collaborators, Stephen Arnott, Mel Goodale, and Jennifer Milne, as well as Daniel, sitting right there. And I want to thank you all for your attention.
Okay, time for a couple of questions. Ned?
In sighted individuals, imagined visual motion excites MT plus as well. Did you try that with the blind individuals?
No. Would be good to do. Yes.
Would also be much easier.
Daniel said would also be much easier, yes.
I'm curious if it's possible that you could make narrative movies for the blind, because you can go out into the environment, you demonstrate it through your method, and actually record the environment. And this actually leads to the conception of virtual reality for the blind. And then one other question. Binaural hearing involves calculating, as I understand it, the distance between the ears, giving information about direction of sound, and you didn't really comment on that difference between the time sound reaches one ear or the other. And could you also comment on how that factors in your approach?
Certainly. I'll comment on the second comment first. Yes, to calculate a horizontal position or direction, the auditory system needs to compare relative timings between the ears. This is well known for source hearing. I would think that the same mechanism, however, also applies in echolocation, because you also infer relative positioning of surfaces in space from the timing differences with regard to the echo in the two ears. There are many other factors that probably play a role, such as spectral differences, intensity differences, and at this point we're just starting to really investigate all the complexity of the signals. In the very beginning I showed you a couple of illustrations, And so at this point, what we're really trying also is to kind of condense this down and to investigate what role all these different parameters may play. As to your second question, could we potentially make recordings in space and use these to create narratives or movies, echolocation movies? When we make our recordings, we typically aim to find conditions that elicit big differences and that are highly salient. This is where Daniel's help is always very important. To make a movie and to create more nuanced narratives and differences, maybe it's possible, but it would be something that we would have to explore in the future.
Last quick question.
Okay, this question could be for you or also for...
Okay, general questions, save them to the end. So maybe let's move on now and take your questions for the general discussion. Okay, thanks very much.
Thanks.
Okay, so our last speaker is finally really going to tell us what it's like to be a bat. So Cynthia Moss has her background was degrees in psychology from Massachusetts and Brown, taught at Harvard, and now for a number of years she's been at the University of Maryland in the Department of Psychology. She's also been director of the Neuroscience and Cognitive Science program there and very active in neuroscience and cognitive science circles. Her research is all about understanding sensory information processing and adaptive motor control, and has really made a specialty of the study of the echolocating bat, which serves as a kind of model for neuroethologically based study of hearing, sensing, and perceptually guided behavior. So, so putting all this together, hopefully we really are going to be in a position to get some kind of understanding of the science and phenomenology of bat perception. So please welcome Cynthia Moss.
Well, thank you very much for the invitation to be here today. I'm afraid I will not be able to tell you what it is like to be a bat, but I will provide some indicators of perception, attention, and memory from behavioral studies in echolocating bats. So, as most of you are probably well aware, echolocating bats produce very high-frequency sounds. These sounds are well suited to bounce off of objects in the path of the sound beam. They return to the bat's ears, and the bat can construct a three-dimensional representation of the world from these echoes. And the bat adapts its behavior in response to the processing of these echoes, and that will be the focus of my talk today, these adaptive behaviors. Now, this is a high-speed video, slowed down, taken from a colony room in my lab, and you see bats flying around here. And in flight, they avoid collisions with obstacles and other bats. They catch moving, often evasive prey, and they can respond to changing environments, all in complete darkness and relying on echolocation. That doesn't mean that bats are completely blind, but they can operate in complete darkness. So successful navigation in complex environments requires 3D localization of objects, spatial attention and memory, and adaptive behaviors. So really engaging sensory, motor, and cognitive systems. And today I'll be emphasizing the adaptive behaviors. So in my talk, I'll begin with a brief introduction of echolocation, spatial localization by sonar, and describe the challenges bats face echolocating in a complex environment. And then I'll go on and describe some behavioral studies that focus on adaptive sonar behavior. I'll describe a study of target discrimination, another of obstacle avoidance and prey capture, and finally one that require bats to sort signals from their own vocalizations and those of other bats. So the star of the show today is the big brown bat, Aptesicus fuscus. It's a North American species, and it's an insect-eating bat. I should say that there are hundreds of bat species that have adapted to very diverse environments, and they use different signals. The big brown bat produces a very broadband, frequency-modulated signal. So it produces a sound that sweeps in the fundamental from over 60 kilohertz down to 20, 25 kilohertz in just a few milliseconds. So this echolocation call is very well suited for spatial localization. So you see on the frequency axis here, on the vertical axis, goes from 100 down to 20 kilohertz, and so all above the range of human hearing, which the upper limit is about 20 kilohertz. So there was just a question about localization using echo, so I'll just say a little bit about that. So bats produce high-frequency sounds, and they listen to echoes from objects that return. So the returning object is, you can think of it as a sound source. And if that object is positioned right along the midline, then the echo returning to the two ears will arrive at the same time, same intensity, roughly same spectrum. And the bat makes a comparison of the cues at the two ears to determine that the object returning the echo arrived from the midline. If, however, an object is off to one side, then one ear will receive an echo before the other ear. It will be a little bit more intense, and the spectral content will be different. And the bat can calculate these, the location of the object from the interaural differences. And horizontal localization accuracy in bats has been estimated to be about 1 degree. Now, bats, like humans, rely on spectral cues to localize in the vertical plane. So what's shown here is spectral measurements taken at the ear of the bat from different vertical positions. So the external ear, see, is very large. There's this structure called the tragus that influences the spectral profile from different elevations. So from 15 degrees above the horizon to 10 degrees below, you see there's a change in the spectral profile, where in this case there's a notch that moves from high to low frequencies with elevation. The details aren't so important, but the idea is that the bat can interpret these spectral changes to estimate the elevation of a sound source. And vertical discrimination thresholds in bats has been shown to be about 3 degrees, which is comparable to humans. Now, bats use the time delay between the sonar emission and the returning echo to estimate the distance. Sound travels in air at a speed of about 340 meters per second. So what that means is for the bat, there's two-way travel time from the bat to an object and back. So there's about 6 millisecond delay for each meter of object distance. And bats can discriminate the distance to objects with very high accuracy of about 1 centimeter, corresponding to about 60 microseconds. This was first demonstrated by Jim Simmons using psychophysical measures, where he trained bats to rest on a platform, and the sounds produced by the bat were picked up by 2 microphones. They were digitized, delayed, played back through speakers, and simulated echoes from objects at different distances. So the delay introduced could create one echo at a closer distance, or an object at a closer distance than another. And the bat's task in this case was to always crawl towards the side on which it perceived the shorter echo delay. And the echo delay difference between the two sides, A and B, was changed from trial to trial. And the bat's performance, if it were just guessing, would be about 50%. But you can see when there's a large difference in the delay or distance between these phantom target echoes, the bat's performance is at about 100%. And as that delay difference gets smaller, the bat's performance begins to drop. And Simmons estimated threshold to be the difference in distance or delay that produced about 75% correct performance, which was about 1 centimeter or 60 microseconds. So just to sum up, sonar localization accuracy in the big brown bat in the horizontal plane is about 1 degree, comparable to humans. Vertical about 3 degrees, again comparable to humans. And along the range axis, they're very, very good and can discriminate differences about 1 centimeter or 60 microsecond delay differences. Okay, so now bats are constantly using this spatial information extracted from sonar echoes to adapt the calls they produce. And I'll show you a high-speed video now taken in the laboratory. The bat was trained to fly and take an insect that was hanging on a tether. So the video and the corresponding sound you'll hear were slowed down by a factor of 16, so you can both see and hear the echolocation calls. There's also a spectrographic display of the sounds. Okay, so the bat will come in from this side here. These are spectrograms now of the calls the bat is producing, these frequency modulated sweeps. So now the bat appears. Locks the head onto the target, scoops up the insect with its tail membrane, and transfers it to its mouth. Now it's continuing to make echolocation calls as it's eating. It can talk and eat at the same time. Okay, so now here's a cartoon to show you sort of the pattern of vocalizations you saw as the bat flying towards the insect. Now, of course, in this cartoon, it's a free-flying insect, not a tethered insect. But each tick mark here represents the timing of a call the bat produced as it moved closer and closer to the insect. So the bat starts in the search phase when it's producing sounds at 5 to 10 per second. Then it moves into what's referred to as the approach phase, and here the calls may be produced at up to about 80 sounds per second. And then finally, during the tracking and terminal phase, terminal for the insect if the bat's successful, the sounds will be produced at 150 to 200 sounds per second. So the bat is continuously increasing the rate of its calls as it gets closer to the target. It's also changing the duration of its calls as it gets closer to the target. You may have noticed that in the video, and this is something I'll be talking about quite a bit today. It changes the frequency content of the calls and the directional aim of its calls, something else I'll be describing. So what I've described so far involves a bat in a relatively simple environment in the open, using these different cues to localize a single object. But the fact is, bats are often operating in much more complex environments, where a single call may result in multiple echoes. So if there's vegetation, multiple insects, at different distances and directions, the bat will receive, for every call it produces, multiple echo returns. And it has to organize this acoustic information, arriving from different directions and different delays. Now, when bats fly together with other bats, they face another problem, and that is sorting their own vocalizations and echoes from those of conspecifics. So now bats, as I've described, adjust their sonar behavior. They make adjustments in the direction, the duration, the frequency, the intensity, and the interval of calls in response to echo information they've gathered from the environment. And these adjustments provide a window to the bat's perception and tell you something about what information the bat has processed and what information it's seeking. And today I'll be talking specifically about adjustments in direction, duration, and frequency. Now, the adaptive sonar behavior of bats contributes to its representation of an auditory scene. The vocal adjustments it makes directly influence the echo returns that determine the direction, distance, and features of objects. It's unlikely that this operates on an echo-to-echo basis. Sound travel in air, so the bat has to produce a sound, the sound travels to the object, the echo returns to the bat, and then the nervous system has to process this echo information and initiate commands for adaptive behaviors while the environment is changing. So it's unlikely this operates on an echo-by-echo basis, but instead the bat will be integrating and updating information over time. And it must be coordinated with spatial attention and memory. So today I'll be talking about adaptive sonar behavior of the bat in 3 different tasks. One involving texture discrimination, one involving stationary obstacle and obstacle avoidance and insect capture, and finally, a task where paired bats competed for a single prey item. So this is the a schematic of the setting used for the different experiments. We have a large flight room. It's about 6 by 6 meters, and the walls and ceiling are lined with acoustic foam, and it's carpeted. Daniel has visited this, and this somewhat echo-attenuating room. We have high-speed infrared sensitive video cameras, so we run our experiments in very low-level, long-wavelength light to require the bat to emphasize echolocation for solving a variety of tasks. We have a microphone array along the walls, and the bat is flying freely, performing in our tasks. We use a microphone array to measure the directional characteristics of the sonar beam. So if the bat's pointing its head in one direction, microphones along one wall will receive stronger signals than neighboring walls, and we can use the relative intensity of the signals picked up by the microphones along the walls to estimate the directionality of the sonar beam pattern, in particular where the bat is pointing its head. The big brown bat produces sounds directly through the open mouth, and so where the sound is directed is also where the head is directed. And the center of the beam we refer to as the beam axis. So in the first experiment I'll describe, the bat was required to discriminate targets. Now, Daniel just mentioned that there is no color in echolocation. There is no color in this experiment. The beads you see here in the pictures show color, but of course this was not a cue available for the bat. In this case, the bat was required to discriminate a smooth bead from one of several different texture beads. So in every trial, 2 beads were hung in the room at random locations. One was always the smooth bead, and one was always one of these textured beads. And the bat's task was to find the smooth bead and tap it. So here's a schematic of the room. You see we have the S plus refers to the smooth bead, S minus the textured bead. We have microphones also on the floor. And in this case, the bat flew around, and then when it tapped S plus, it received a signal, a tone, that told it it could fly to a landing platform and receive a food reward. If it didn't tap the smooth bead, then it didn't get the reward. Okay. And now here's a quick video to show you a bat actually performing in this task. It's been slowed down so you can see the bat's flight behavior and hear the echolocation calls it produced. You can pay attention to the times when the bat increases the rate of its calling. There. So it approached the targets but then flew past. So remarkably, when the bat performs in this task, as it approaches and taps that bead, its behavior is very similar to what it shows as it intercepts insect prey. Now, here is a slide to show the performance of the bat as it discriminated different beads. So you see percent correct performance for these different beads, and some beads were very easy for the bat to discriminate from the smooth, others not so much. This is not what I want to emphasize today, but instead the animal's adaptive behavior performing in the task. So we found in this task that the bat made changes in its calls with respect to the direction and distance of the objects. And we can use the adaptive changes to get some estimate of the animal's acoustic gaze. And here I'll be describing the beam aim, the directional aim of the calls, and the temporal characteristics of the calls. So now here's an animation of a single trial in which a bat is flying and searching for the smooth bead. You see the bat flying. Each time it produces a call, you see a circle displayed. Below here, the interval between successive calls and the duration of the calls as the bat performs in the task. So you see now it's approaching the two targets, begins to increase the rate, then there's a gap, flies around that one bead, and turns to approach and tap the smooth bead. Okay. Now, perhaps more informative are the directional characteristics of the call as the bat performs in this task. So here you'll see the same trial. Bat will be flying. You see it's an overhead view, and you'll see the beam pattern of the calls produced by the bat as it approaches and taps the S+. That's the S minus, flew past it, turns, and taps the smooth bead. There is no, on this particular trial, there were no microphones here, so there's some distortion in the beam aim reconstruction, but the bat did direct its beam at the bead. Now we can actually compute a tracking angle, that is the angular difference between the beam axis and a target or obstacle. And so from this trial you just saw, the tracking angle is plotted, and when the circles line up with this line here, the beam is directed at the target, and when the beam is directed at the distractor, you see the circles clustered here. So you see the bat directed its beam at the target, at the distractor, and then back at the target. Now, I've talked about how the bat controls the timing of its calls. So as it's approaching an insect or a bead, when it's far away, the calls are longer, and when it gets closer to the target, the calls are shorter. Now, why does the bat adjust the duration of its calls in this way? Well, we believe it's to avoid overlap between its outgoing calls and the echoes returning from objects. So this is just illustrated in a cartoon here, where if we have a call, a pulse of a given duration, and there's an object very close, the echo will overlap with the vocalization. However, if the bat shortens the call, then it can temporarily separate the pulse and the echo, and the bat actively does this. So these adjustments in the call duration give us some indication of where the bat is attending along the range or distance axis. So now I'll show you the same trial, the radius of the beam pattern now has been scaled to the duration of the bat's call. So you can get some indication of where the bat is attending as it's performing the task. The sticks represent the beam axis. So from this animation, you really get a sense of the bat looks at the distractor, then decides to fly past it, and then taps the S+. And that's just illustrated in this slide here, where you see different segments in time. The bat's approaching one, the S-, decides to fly past it. At point 2, the call duration is increased as it's looking beyond that target, and then shortens the calls again as it approaches the S+. So in these experiments across many, many trials that were analyzed, we find that the bat accurately points its sonar beam in the direction of objects, and it controls the sonar duration with respect to the range of targets. Now I'll describe another task that illustrates essentially the same thing. In this case, the bat has to deal with an obstacle and a target. So here again is our flight room, and in this case we have a net stretched across the room with 2 openings, and the bat has to find a tethered insect behind one of these 2 openings. There's a partition net that divides the back end of the room to keep the bat honest. So it has to look for the appropriate compartment housing the reward to receive the food. So here's a trial that shows the bat performing in this task. Again, each circle represents the bat's position when it produces a call. See, as the bat approaches the net, it's reducing the interval between calls, reducing the duration. Before it flies through, increases the duration, and then shortens it again as it takes the tethered insect. Now here's the beam aim for the same trial. So now here you can see the sticks again represent the beam axis where the bat's pointing its head. You can see that it directs the beam at the edges of the net opening, shifts back between the left and the right sides, then points the beam through the opening, and then locks the beam onto the target. And that's just shown here for this particular trial. The bat looks at one edge of the net, the other edge of the net, back to the one edge of the net, and then the insect. So we see this sequential pointing from one object to another, even though they're very closely spaced, and the beam is broad enough to capture echoes from these closely spaced objects. The bat intentionally points its beam, like we point our eyes at objects of interest. Now here's one more trial that very clearly illustrates this, and here also note the changes in the duration of the calls the bat produces as it first approaches the net. See, the calls are short here, and then before it flies through the net, it's already begun to increase the duration of its calls. It's looking beyond the net, the obstacle, to the more distant prey item. And this slide shows data for across several trials, the time which the bat locked its beam onto the worm, plotted against the time at which it first experienced overlap between its vocalizations and the net echo. The time 0 refers to the time when the bat flew through the net. So these data show that the bat shifts the distance of its acoustic gaze at different times in different trials, but from the obstacle to the target. So what I've shown so far is that the bat makes adjustments in sonar signals to actively separate and track objects in the auditory scene. The aim of the sonar beam axis facilitates segregation of objects in different directions, and the duration of signals facilitates the segregation of objects at different distances. Okay. Why does the bat sequentially point the sonar beam at closely spaced objects of interest? Well, we don't really know, but we have some speculation. And one is that the localization accuracy be highest along the midline, and it may also play a role in motor planning. But as I said, it's probably not driven by detection because the beam is really wide enough to capture echoes well off axis. Okay, so the implications of the sequential pointing of the sonar beam is that the spatial attention shifts with the directional aim of the sonar beam, and that working memory must operate to assemble echoes over time to build a representation of the auditory scene. Okay. Now, I was going to say just a little bit about spatial memory and the use of landmarks, but I'm running a little short on time, so I can come back to this later if people have some questions. So I'll skip over these slides and just briefly tell you about the experiment in which 2 bats competed for a single prey item. Now, we use the same room, and we have multiple microphones on the floor that play an important role in allowing us to assign calls to the vocalizing bats, because it's a really kind of a mess. Here's a short snippet of calls recorded from 2 bats, and if you just look at this, it's very difficult to say which bat was vocalizing when. But with the use of our video cameras that tell us the 3D position of the bat in the room, and the microphones that tell us about time delays of sounds produced by animals in different locations, we can accurately identify which bat is calling at any point in time. I won't go through the details here, but we did successfully do this. And what we found is when these bats were paired, competing for a single prey item, they showed two strategies. One, adaptive increase in the call design separation. So the bats, when they flew alone, we looked at the calls they produced and characterized them, and then we paired them. And we saw that they could make adjustments in their call design, and then we also found that bats sometimes went silent. So I'll show you an animation that illustrates both call adjustment and silence. So each of the bats is shown in a different color. And remember, when the bat produces a call, there's a circle displayed to show its position when it makes that call. The interval, duration, and frequency of the calls produced by the two bats shown below. Okay. Okay, so that sneaky red bat was silent for a long stretch and then snuck up the last minute and took the insect, and the poor blue bat was a little bit mystified, didn't know quite what happened. Okay. Now we've measured the parameters of the calls, as I mentioned, in baseline when the bats were flown individually and then when they were paired, and we found that bats with similar call design increase the separation between the acoustic parameters of their vocalizations, and bats that had dissimilar call design to start with didn't bother. And that was true for all the frequency characteristics that we measured. And what's shown here is just the magnitude of the start frequency separation, large and small. It's a function of the baseline start frequency separation. So when they already showed large differences, they didn't bother to make adjustments. But when they didn't have large differences to start with, then they made adjustments when they were paired. And the magnitude of the adjustments also depended on the separation between the bats. And I'll just say a little bit about the silent behavior. Okay, in bat time, 200 milliseconds is a long time. Okay, between the time of detection and capture of an insect is often less than a second. So we define silent behavior as one or both bats ceasing vocalization for at least 200 milliseconds. And this was almost never observed in bats flying alone. However, when bats were paired, we observed it 40% of trial time when the bats were separated by a meter or less. And we found that the mean distance covered by bats during this silent period was 1.5 meters, but it could range up to over 7 meters. We found, like the adjustments in the vocal behavior, the characteristics of the calls, the silent behavior depended on the spatial separation between the two bats. We found the most silent behavior when the bats were very close together. And we also found that the prevalence of silent behavior depended on the baseline similarity of the calls the bats produced. So when the bats showed very similar call design, they showed more silent behavior than when they showed dissimilar call design. And we also paired individual bats with more than one bat, and their silent behavior depended on the similarity of the calls of the bat with which it was paired. So if the bat showed low similarity to an individual it was paired with, it showed less silent behavior than when it was paired with a bat for which it had high similarity. So these letters here, HP54, Y31, they refer to the individual bats, and you see for each of the individual bats there's an increase in silent behavior when it's paired with another bat with more similar calls. So now, just to sum up, apologize for running over. A silent bat listens passively and analyzes the auditory scene by listening to calls of the neighboring bat and by listening to echoes from the calls of the neighboring bat. bat, but it's really an open question. Can the bat obtain detailed spatial information about auditory objects when it listens passively? And we should note that in the task, when the bats were going after a single prey item, the bat was never silent just before attempting capture of the tethered insect. So the bat's vocal behavior in complex environments suggests that it segregates and tracks dynamic auditory objects by actively controlling the echo information it uses to analyze the scene. The direction, it controls the directional aim of the beam, and it sequentially inspects closely spaced objects. It controls the duration of its calls to shift gaze along the range axis. It controls the frequency of its calls to avoid signal jamming. And collectively, these adaptive behaviors serve the bat to operate in a complex environment. So what is it like to be a bat? I'll leave that to you. Acknowledge that there are many people who contributed to the experiments I described today: Jana Barcelo, Chen Chu, Ben Falk, Koshi Ghosh, Anne-Marie Serlicke Wazon, and Scott Livingston. And thank you.
Okay, let's thank Cynthia again and then open it up for group discussion. So let's see, do any of you have questions or comments for each other that you want to bring up? Or should we? Anything?
Probably.
Daniel, do you have any thoughts about Cindy's allures or vice versa?
I sympathize with the bat. I mean, I can say that when it comes to bat behavior, when we examine the bat behavior and we look at the bat's adaptive echo signals, I certainly feel I understand why that's happening. We do see many analogs in human echolocators. For example, I call it targeting sonar versus orientation sonar. So orientation sonar is you're walking along, you're navigating along, you're simply keeping track of where you are. You're probably clicking less frequently and more loudly. But for targeting sonar, which involves some kind of interception of an object, be it for avoidance or retrieval or recognition, you're probably clicking more frequently, often less loudly, so as to enable you to focus in more effectively on the target and increase its signal against its background. So that's just one example of how a human echolocator might respond to its environment in a manner somewhat similar to bats.
So on this question, Daniel, of what it's like to echolocate, I'm curious about the relationship between your echolocation spatial sense of the objects around you and the auditory experiences that you're having from hearing the background clicks and so on. I mean, do the clicks and so on just totally disappear from the phenomenology? Are they related in some ways to the spatial sense, so the space is somehow imbued with clicks, or is it some relationship that's different again?
You do hear the click. You can't really factor it out of one's consciousness very well. So if I'm clicking, I'm definitely hearing the click. However, I will say that many people who echolocate are, in fact, not always conscious of their clicking. So I have, or indeed of other sounds that they might be making. So I have worked with individuals who are producing signals, presumably for echolocation purposes. There would seem to be evidence of that. And yet, when questioned about this, they report not having been aware that they've been producing signals.
So is there any auditory element to your spatial sense of your surroundings when you're navigating by echolocation? Is there any sense in which it feels like sound at all, or is the clicks just separate from the spatial sense?
I'm now thinking I'm not understanding your question. There is an awareness of sound when echolocating, but I think that different people have different phenomenological awarenesses. Some people report or verbalize their experience in more visual terms, flashes of light, dark shadows, dark curtains. Other people actually talk about their experience in with more tactile language. And others might use more auditory language. And I think it might depend a bit more on learning style. It might depend a bit more on background experiences. Individuals who have not had previous visual experience may describe their environment in visual terms. Well, they may describe their environment in rich spatial terms, which have visual language, but they're not likely to use terminologies like dark curtains or shadows or flashes in that same sense.
I don't know whether either of you want to comment on this question of the extent to which echolocation is, phenomenologically or otherwise, like vision, and the extent to which it's like hearing.
Well, I would say in the case of the bat, it responds so rapidly and can maneuver through tight spaces so agilely that I see this as strong evidence that it has a very rich spatial representation, like vision.
Laura?
Yeah, I would also, so I think that there are also certain properties of the echolocation derived information that are very similar to visual information, such as certain spatial layouts. Other types of information, however, cannot be obtained, or at least they're more ambiguous. For example, Daniel mentioned that echolocation can also be used to obtain information about substance of the sound reflecting surface, such as, say, a piece of wood versus a spongy material. They will give rise to very different acoustic reflections. And in vision, we often think of the surface material and the shape of a surface very independently, even though they may be less independent than we think. But in echolocation, they're perhaps even more intricately linked, because the shape of a surface, and when a surface is, say, convex, will give rise to a fainter echo as compared to a flat or a concave surface. And however, one can then create a similar acoustic reflection by just changing the material. So in this way, I think we really have to rethink, or at least I had, let's say, I talk now about myself, I really had to reconceptualize the way I think about what the actual information is and how this relates to the physical entities in space.
Okay, and now we can open it up for a general question that you had there in the reaching up. Had a general question? Yeah, no, well, yeah, in the blue. Is it blue?
Yeah, you asked the question that I had. I wanted to sort of add something to that question, which is, it seems that radar echolocation and visual reception of waveform information from the environment all works on the same two-dimensional limitation of triangulation, where the information is triangulated to us, and if there's something completely blocking some information, then it can't triangulate to us. And so it makes me wonder how similar, maybe for Daniel, maybe you could speak to this, how similar the mental construct that I build in my mind from all of this triangulated waveform, it's flat because it's 2D, but my mind creates a 3D model of it, and I can perceive depth from this triangulated information. And do you see the two ideas of a sort of flat way of looking at the information, if you wanted to look at it flat, and also an extruded or a depth-based way of looking or interpreting the information, the model that you have? Can you see it in both ways?
I don't think so. I think it really seems, I think if I thought about it, I could. And I've thought about it a lot. But typically as a person echolocates, they're not necessarily thinking about it to that degree. They tend to be just aware of a three-dimensional experience. even though they may be clicking and scanning. So clicking and scanning for humans is much the same with bats. You're scanning with your signal, you're moving your ears in the same way that you would be moving your eyes. And the stimuli that are received are integrated into the brain, really into one image. It's much like retinal saccade. I mean, vision does really the same thing in terms of, or a similar thing in terms of how it moves its retina, how it scans its retina. Even if you try to keep your eyes perfectly still, your eyes aren't perfectly still. There are elements in your eyes that are constantly in motion, taking snapshots, if you will, of the environment, and the brain zipping them together into a composite image. So I'm not sure that I think the situation is similar to some degree with echolocation.
I have two quick questions about human echolocation. So one is what advantage non-sighted people have to achieve this echolocation? So obviously they're more motivated, but if we can subtract the motivational difference, are sighted people, can they learn to do this as well as non-sighted people or not? And the second question is, when sighted people achieve this, should we expect that this is achieved by visual areas of the brain or not?
Should we split the question? Yeah, so I could maybe talk to the second question, then Daniel can answer the first question. So based on the way I think about it, I would say yes. I would expect or predict that sighted people learning to echolocate would also recruit visual cortical areas to do so.
Yeah. The motivational factor is actually quite important, as is the necessity for regular practice and application. So assuming that you were somehow able to make a sighted person motivated and put them in a situation where they were able to practice this regularly, maybe you blindfold them for a month or so, yeah, a sighted person could learn this. Many sighted people take longer at first because it would seem that the auditory system needs time to adapt. So the auditory system needs time to refine, I would guess, its temporal and frequency calculations to be able to receive, well, to be able to process the data that are received. The auditory brain in a sighted person seems to be either unaware or just dismisses a lot of this data. One of the issues that Laura talked about earlier was the precedent effect. Okay, so you have to learn to undo the precedent effect for one thing. And that takes a bit of jiggery-pokery in the auditory system probably to be able to do. And once you've made those adaptations, then yes, I don't see why not.
So there is evidence that normally sighted people use echolocation already in some context, right? Like, you know, blindfolded, walking down a corridor, people don't bump into walls and so on. So I take it the potential is already in some sense there.
As I mentioned earlier, I think it is hardwired. I think it's just a matter of activating that system.
And we use echoes without necessarily being aware of using echoes. We're all aware, or we have a sense of this room, the size of the room, from the reverberation.
This is a question for Daniel. Do you use echolocation in your dream?
Yes. Yes. So basically, our dreams are representations of our reality. So and to some extent representative of how we perceive reality. So my dreams are as I perceive reality. They're based on touch, they're based on hearing, they're based on echolocation, they're based on language, they're based on all of the things that my reality is based on.
Daniel, have you had the opportunity to work with young children, and do you find that they're any faster at learning echolocation or able to learn it more fully? And then also, have you had any blind students who have been unable to learn echolocation? Do you have any knowledge or speculation as to why, if so?
We work a lot with children. Probably 75% of our clientele is children. We've worked with children as toddlers and infants, so very young children. I would say yes, they are more adaptable, they're more flexible. In that sense, they learn echolocation faster. They learn just about everything faster. But I think that the real index here is motivation. It's motivation and practice. It's very difficult to teach a child anything if they're not motivated and they don't practice. And as far as, yes, we've had a few blind people who really, really seem to struggle with echolocation. But we have to keep in mind that there are two elements here. One element is the actual auditory perception of differences. We have had children individuals, able to perceive the echo distinctions quite effectively, but not necessarily effectively apply that to movement. So it's one thing to be able to perceive the information. It's a different matter to then apply that information to governing your movement more and more effectively. So sometimes we've had students able to perceive things quite well, but not able to apply that to movement. Possibly they're not imaging effectively. So they're hearing the distinctions, but they're not actually imaging those distinctions. And then by consequence, they're not able to apply that image to effectively governing movement. Some individuals just do have difficulty hearing the distinctions. So for whatever reason, they may have trouble being aware of those auditory distinctions. Maybe they have an auditory processing issue of some kind. There are blind people who have auditory processing issues, just like there are sighted people who have auditory processing issues.
Alexander.
So, yeah, two aspects. First of all,
just one. Time is running out, so just ask one question.
Okay. No, it's one question with two aspects. So, first aspect, did you consider what happens in a musician's brain when he's reading a score, a music score? Secondly, did you consider what's happened in a conductor, orchestra conductor's brain when he's conducting? Because conducting means to anticipate the results of written score with the real sound, which is an echolocation, anticipated echolocation. Did you consider this aspect?
Was this the question for me? I'm not sure I understood the question in its entirety. If you could
The fact, explain, when a musician read a score, just read it,
Alexander, try it without the microphone. Just shout.
when a musician read a score, automatically in the brain, very short, the sound is represented, not one sound, whole sound. Did you
when musicians read the score?
Yes. And so the question is whether there's a similar expansion of the anticipated sounds in echolocation. Is that correct?
Yes and no. Yes and no, because this is the mind producing the sound, anticipating what the real sound will come.
I think maybe we'll take this as a contribution and move to the next question here. Thanks.
I think anyone who's listened to a stereo system or a home theater system has had the illusion of motion from one side to the other. Have any of you either discovered or have used audio illusions in your work?
So I have not used illusions so far, but for example, so we are aware that these things happen, and for example, to take care of it, the way we, for example, design our stimuli is to make them as close to the real thing as possible, which would then include make the recording that the person would hear it. Should answer, yeah.
Thank you. I want to ask Laura, since you dealing with blind people, there is attention is ruled out. Then intention and the intuition could be that which direct the echolation. In a sense that we now establishing a theory for the intelligence of the heart, and the heart, of course, processes information, the heart receives information. And from the environment, there could be an electromagnetic waves that receive or that information to the heart, and the heart signal to the brain. And in fact, when you hit this echolation, is a conscious act. And correctly you said that you are not dealing with the unconscious, you're dealing with the conscious act and consciousness. So this, the theory of the heart is quietly, nicely can fit in your direction. Thanks.
Thank you. I think Ned has another question. Does anyone want to comment on that?
So as I'm sure you're well aware, in sight there are two visual systems, a system at the top of the head that processes very quickly and supposedly largely unconsciously, is much more spatial, has egocentric representations as compared with the so-called ventral visual system, conscious, slow, allocentric representations. In the case of echolocation, either in bats or in humans, does that correspond more to the dorsal unconscious system or more to the ventral conscious system, or does that distinction not make any sense, or what?
So there are certainly many visual streams, the most prominent distinction between the dorsal and ventral. There's a debate, of course, to what degree they serve different functions. We actually investigated potential different neural substrates for different spatial properties as could be derived from echolocation, and there seems to be evidence that, for example, attributes such as locations and so on activate more parietal areas which might be considered a part of the dorsal stream, whereas attributes such as shape, regardless of the location of the object, might be more processed in ventral visual stream areas. But this is work in progress.